Okay, this is the fourth question on the energy packet. This one's not too crazy. I mean, some of these answer choices, one of them in particular, is pretty whack, but otherwise, it's actually not that bad. So, what the question is stating, right, is that the block is oscillating along this x-axis. It's going from point A to point negative A, and it's in between. It's going to hit zero. And the most important part about this whole question, honestly, is the fact that it is a horizontal frictionless plane. Honestly, just frictionless plane is enough. And this is similar to that one question we had earlier in the packet where it talked about negligible air resistance. And the reason for that is because it's a frictionless plane, that means it's a conservation of energy. You can't even tell that says energy. Oh my god, bro. It's a conservation of energy scenario, right? And essentially what that means, right, is if we have 100 joules of force right here, it means we also have to have 100 joules of force right here. So I'm going to actually stick with that 100 joules and just kind of use that to help illustrate what I mean by conservation in this scenario, right? So 100 joules of force, and it's up to us to kind of allocate and see, okay, well, how much of that force is elastic force? How much of that is kinetic force at each of these individual spots? Because the answers are just kind of asking us, right? At x is equal to zero, at x is equal to a, how much of so and so energy is there? Uh, you know, it's kind of just saying, okay, well, at x is equal to a, the elastic potential energy is at a minimum, right? At x is equal to o, the elastic is a minimum. So you have to just kind of see, okay, well, based on what they're asking us to solve for, that being elastic and kinetic, how much of both of those are at every point? So because of that, I'm also just gonna go ahead. Holy, can I speak English, please? I'm gonna go ahead and write down our formulas. So for kinetic, that's gonna be 1/2 mv squared, and for this is a u, by the way. For spring, that's 1/2 kx squared. Um, so those are our formulas. This will come in handy towards the end. But for the most part, we have to kind of establish like, okay, this is what we're looking for. Um, and at point A, I'm gonna start at point A. At point A, right? If the block is over here, this means the spring has stretched all the way out, and it can no longer stretch anymore. If it's oscillating from here to here, and it's going back and back and forth, it means the box can no longer go this way because the spring is fully stretched out. This means once the box hits point A, it's about to switch up and go all the way to the left. And in that instant that it switches up, that means that it's stopping. The velocity would be equal to zero, right? Because it's changing direction. Essentially, that means that if we consider our two formulas up here, if v is equal to zero and we plug in v right here, or sorry, we plug in v is equal to zero right there, that's going to nullify all of our kinetic energy. And that means out of our 100 joules, all of it is going to be spring. The energy has to come from somewhere, right? And if there's quite literally no movement happening at point A, it cannot be kinetic, which means our only option left is that it's going to be potential. That makes sense. If you were to hold the block, if you were to hold it still here at point A and stretch the spring all the way out, you would feel a lot of tension. And the second you let the block go, it would fly towards the left, right? And that's because there's a lot of potential energy being stored up in that spring. So that basically just means 100% of our energy is equal to U as in like potential spring energy. The same applies for here as well. I mean, at this point, the spring would be at its shortest, like it physically cannot compress any smaller than this. So the box again is not moving. So that means 100% of the energy is U. So that leaves the middle part. And the middle part is honestly kind of annoying to explain just because when you look at the picture, you see this spring and you see the box right here, and you kind of assume for a second, okay, maybe it's at rest. But in reality, this box is constantly moving side to side to side. But the moment the box reaches this point of x is equal to zero, the spring is not distorted in any way. It's not stretched out like that. It's not compressed. The spring is basically reached equilibrium. It's not changing shape at all, which means all of the energy the box is experiencing at this point has to be kinetic because if the spring is not applying any force on the box, then it can't contribute to the joule. It can't contribute to the energy in any way, right? If the spring is quite literally not pulling the box to the left or pushing it to the right, it's not doing anything, which means um, all of the energy here is going to be kinetic. You can explain this by plugging in 0 as well for displacement, because when you look at spring constant or the spring formula, it's 1/2 spring constant times um, the displacement of x. But again, if the spring is not stretched out or compressed, there's no displacement occurring. It would just end up being 0, which would cancel it out fully, which is why for this middle point, our kinetic energy is actually 100% of the joules goes towards kinetic. Okay, just said. I don't know why I said like that, but yeah. This means at point A, it's not moving and it's fully spring. At point 0, it is moving, so it's fully kinetic and there's no spring acting on it. And at point negative A, it's fully potential spring and it's not moving, so it's stopping here before it shoots back towards the right. Doing that. Okay. So looking at our answer choices now, um, yeah, I'll just start with A. I mean, okay, I'll be honest. The answer is just A. Pretty flat out. If we just look at it, it tells you, right? The potential spring energy being at a minimum at x equals 0 makes sense, right? Because like we just stated, at x equals 0, the spring is not experiencing any displacement, which means we plug in 0 into the formula, which means there's no elastic potential energy. The only energy the box is experiencing is its own kinetic energy as it flies from the left to the right. The second the box moves even a tiny bit to the left, or like to the left, for example, now the spring is compressed just a little bit. And maybe we can say, okay, 20 joules goes towards elastic potential and 80 joules goes towards kinetic, right? But for now, we're just looking at x equals 0. At x equals 0, the box is moving fully on its own. The spring is not stretched, it's not compressed, so the displacement is 0, so it can only be kinetic, which means the elastic potential would indeed be at a minimum at x equals 0. For B, the elastic potential energy of the box is at a minimum at x equals a. This would actually be the opposite. This would be the maximum, because like we said earlier, right? If the box is not moving at point A, the velocity is going to be equal to 0, which means there's no kinetic energy occurring. It's purely going to be elastic potential energy, which would have to be at a maximum, right? If there's only elastic potential energy, it would have to be all 100 joules. So it'd be at a maximum at point A. Uh, Answer choice C is actually just the opposite of A. This would again have to be maximum for it to be correct, but essentially the kinetic energy is at its highest when there's no spring energy impeding on it. And at x is equal to 0, there is no spring energy. So all of the energy again has to be kinetic, which means this would have to be maximum. For D, again, also not correct because at A, right, at A, there's no kinetic energy. It's not moving. The box is changing directions and it's about to, it's experiencing a lot of potential elastic energy, but it's not going to be experiencing any kinetic because it's, again, standing still. So it can't be D. This is honestly as far as I would want to solve it just because E is like a pain in the butt. Um, so yeah, just based off this, A is going to be the correct answer. But I will just kind of cover E. The way I learned to solve this, I did not learn in class, and I don't even know if we covered this in class. We could have. Honestly, I don't listen that much, so maybe she's mentioned it, but I did not hear it. So this might be a foreign concept. But anyways, um, the way you solve this, right, is you have to set the kinetic energy equal to the elastic potential energy. And so we just kind of set our formulas equal to each other. It's going to be kx squared. But the reason this is kind of different is because this is not the actual formula we use. For spring harmonic motion, which is like when the spring is moving back and forth, you actually end up using a different formula for kinetic energy. Again, we might have learned this, but I don't know. But the reasoning we use, I'll explain like what you're substituting in. But essentially, for angular frequency, we have this symbol. It's like a little curly little W. And this is equal to the square root of k divided by m. And when we consider W in the scope of velocity, um, velocity is equal to actually plus or minus square root a, and a is in reference to uh amplitude, right? A amplitude minus x squared. So this is what our velocity is kind of equal to. Or sorry, I messed this up. Let me forget what I just said there. This is actually equal to velocity equal to plus or minus w square root amplitude squared minus x squared. Again, this probably won't even be necessary on the test. I just want to explain why it's not E and like fully solve it out. But again, this is kind of what we're dealing with now. So we actually have to plug this V into our equation, like our standard kinetic form equation. So I'm gonna just pull this up here because spring is its own thing. But that means that K is going to be equal to 1 half M times W squared A squared minus X. So this is just us like plugging it in. And then since W squared is equal to what I kind of mentioned up, and we're squaring W, by the way, just so we don't have to deal with the square root sign. Because this would just be equal to that, we're going to end up plugging that in. So we end up getting K is equal to 1 half M times K over M, and then you get A squared minus X squared, because we're taking this and we're sticking it in this equation over here. And then after that, you just kind of cancel out the M's. Oh, where's my mouse? Okay, I'm good. You cancel out the M's. So this one goes away, this one goes away. You get K is equal to 1 half K A squared. It's a capital A, sorry. Capital A minus X squared. So this ends up being our kinetic energy formula. And you can set this equal to 1 half Kx squared, which is our what is it? Elastic formula. And the reason this is like done in general is because when you plug all of these other values in, like these different constants, you end up like with you're left with K, right? And since you have K on both sides, it makes it a lot easier to figure out. So when you're solving questions that have spring, I guess sometimes you use this, but God knows if this is on the AP test, if this is what we're supposed to be doing for this packet. But this is how I was taught by my tutor to do it. So now these are set equal to each other. We just quite literally just have to solve. So you cancel out the 1/2s. And let me think. So let's do V and we cancel out the 1/2s. Or what do we do at this point? I'm trying to think. I want to make sure I explain this correctly. Because I don't want to just cancel out the K's blindly. This You're gonna have to bear with me for a sec. Okay, yeah. So you're gonna cancel out the 1K actually on both, right? They're the same freaking thing. So you're gonna be left with a squared minus x squared is gonna be equal to x squared. And then we just kind of solve it further, right? So we move this to this side. So a squared is equal to 2x squared. And then you divide both sides by 2. So you get, what is that? A2 over 2 is equal to x squared. And then you just square it. Square root it. So then you get square root of a squared over 2 is equal to x. And this is our final answer. And, oh, sorry, because we are actually square rooting that, it's be plus or minus. So this is our, I guess, quote unquote, final answer. Or, sorry, what am I doing? Because we square rooted that, it's just going to be a over square root 2 plus or minus. Because again, like if you square root the whole thing, right, this cancels out, this becomes a, this becomes square rooted. So it's going to be plus or minus a over square root 2. This is not necessary, I don't think. But the reason I'm doing this is because this is going to explain what this is essentially saying, right? This is saying the kinetic energy of the block is always equal to the elastic potential energy of the spring. The key word here is always. By solving this equation, what we're basically saying is that no, it's not always equal to each other. They're only equal to each other at the position plus or minus a over square root 2, which that's, that's going to be somewhere here, right? That's why it's plus or minus, right? It's somewhere on the plus, somewhere on the minus. That's when they're equal to each other. That's when it would be 50 joules elastic, 50 joules kinetic. It's not going to be always though, which is why the answer cannot be E. Again, I don't think you actually have to do all of this. I highly doubt. Like, I do not remember. Like, truthfully, no way did we learn this in class. But TBH, I was not listening. So maybe she did cover this. I have no memory of that. So this might not be necessary, but I just want to kind of go ahead and explain why it cannot be E by fully solving it out. Essentially, what it's saying though is if you set them equal to each other, the only time that they are equal is at plus or minus a over square root 2. And because that is not always, it cannot be E. So our answer has to be A.